what we're going to do is we're just going to look at an instant in time, right? So this simulation is frozen. I'm not playing it, so nothing is going to happen. Nothing is going to change. But what I want you to see is as I increase the angle of this ramp, you're going to be able to see the force of friction here on a free body diagram. It looks just like the one that I made. And the force of friction shows up again here. Again, it's the same free body diagram. And as I increase this ramp angle, look at what happens to the force of friction. For a single block in a single spot with a single mass, you can see that the force of friction increases as you increase the angle of the ramp. That's what I told you in the last video. But here's what's interesting. Watch what happens as I get past a certain spot, and then all of a sudden, it starts to go down. So that seems weird. So what's going on there? Why is that happening? Yeah, Lynn?
The friction can never be greater than the normal?
Well, that's not true. It's greater than the normal right here. Yeah, it can be greater than the normal force. Absolutely, it can be greater than the normal force. A great example of that is a piece of tape. If you take a piece of tape and put it on a table, then the force it takes to lift the tape straight up is much less than the force that it takes to pull that tape horizontally. But friction is much stronger than the normal force there. Here's what's going on, is that when you get to the point that it starts to move, and all of a sudden there's a net force. See that net force? All of a sudden there's a net force. That's when everything starts to crumble. And it'll make a lot more sense if I start the simulation so that it's no longer a instant in time. See what happens? As soon as that friction force jumps, that's when the motion starts. So the key here for you to see is that as you raise the ramp for an object that is not moving, the friction force will continue to increase and increase and increase and increase until it hits some maximum. It can't be any larger than that. That means the object starts to slide, and as soon as that happens, everything that we just did breaks. We no longer can say that friction is going to be equal to the weight of the object times the sine of the angle. It's not anymore. Those forces aren't balanced anymore. Now there's if we move it back up on the ramp, now you can see there's a net force here, right? As soon as we get this ramp angle high enough, there's a net force now. The sum of the forces in this x dimension, in this parallel dimension, will be equal to the net force, not zero anymore. So that breaks a whole bunch of other stuff, right? And then the other thing that I want to ask you about is what did you see? What have you seen so far? How many of you have had a chance to collect data and evaluate data for the weight? Just changing the weight of the object and nothing else. Does anybody have a report for that yet? Or if you're still working on it, that's fine. Caleb, what did you see?
It was a bit weird. It did appear that there is a correlation between maximum friction and object experiences and that object's weight.
It looks like you get more friction for heavier objects. So that tells me that maybe your angles changed a little bit, but not not that much, right?
It still changes though. Like
Yeah.
It took less of an angle.
Yeah, and that's one of those real life things, right? Like the truth of the matter is, reality is complicated. And so it might be that under ideal circumstances we might see one thing or the other, but when we have reality, things get a little bit complicated. So we're not gonna deliver a verdict on that yet. What about the surface type? Did anybody here do an evaluation of their surface type data? And if so, what did you see?
I mean, it seemed like it took a little, like a bigger angle with like the sandpaper, for example, than like the wood.
Okay, so at least one group did seem to see something that appeared meaningful, right? Like if you raise your ramp to 10 degrees with just the wood surface, and then you raise it to 11 degrees with the sandpaper, I don't know, maybe that's meaningful, but maybe not. But if you're going from 10 degrees to like 18 degrees,
Yeah, it wasn't quite that extreme,
Yeah.
the numbers were really small.
what was it? What were your numbers?
I think
Well, it's okay, no, it's all right. But if you, yeah, just if you happen to know them, that's great. But
There's like, it's like a 0.1 Newton difference between bare felt and sandpaper.
Okay, 0.1 newtons, but what was the total friction?
For the friction?
Yeah, was it relatively small?
Yeah.
So what was the force of friction
For
any of them?
0.3.
So 0.3, so you're saying the difference was about 0.1, but like the kinds of frictions you were getting were only about 0.3. So 0.1 divided by 0.3, that's like 30% difference. So that's somewhat significant, right? 30% might be meaningful, right? So that's great. What about the surface area? Did anybody have an evaluation for that, or at least a preliminary evaluation for that?
It
Rich?
appeared to be roughly the same.
Roughly the same, yeah. So, I could tell you, and on Monday, we're gonna talk about what it looks like theoretically. Theoretically, the weight should matter. The increase in friction should be proportional to the increase in weight. Theoretically, the surface type should matter, not necessarily in a way that's predictable. Like you might look at two surfaces and be like, well, there's gonna be a lot of friction there, and be wrong, but it should be consistent. So if one surface type has 10% more friction at a given weight, it should have 10% more friction at some other weight, okay? And then the surface area, again, theoretically, should make no difference at all. Surface area should be irrelevant. But what you should be seeing, what I would expect that you're seeing, is that because this is real data and real life scenarios and a lot of imperfections in the materials and the surfaces and your ability to make measurements, this is gonna be a little bit more ambiguous. And it may be that there might even be disagreements, like some of you might be like, well, we got more friction with the sandpaper, and others may say we got more friction with the felt, which may have to do with the quality of your work, or it may have to do with the fact that one person's sandpaper might have been different than another person's sandpaper, or one person's felt might have been different. So there actually might be, some of those felt blocks might have more friction than some of the sandpaper blocks, but some of the sandpaper blocks might have more friction than some of the felt blocks. We wouldn't know unless we looked at each little piece of sandpaper separately. So I think what we'll do, we'll kind of do some wrap up on Monday, and I think what we'll do is I'm going to try to be real prescriptive about what I have you do, so that ideally we get some really good solid measurements, and we can draw some more meaningful conclusions, right? So if you haven't done this yet, will you take a picture of what you can work for a couple more minutes, but before you leave, take a picture, whatever you've got, and turn it in. We will keep discussing this on Monday, but this is the last official day for this assignment in class.